Okay, so now we need to have a look at simple harmonic motion, which is a form of oscillating motion. We call it SHM for short. And simple harmonic motion is any oscillating motion that obeys the equation A equals minus omega x. So A is for acceleration. Omega, like we saw in circular motion, is the angular frequency, and x is the displacement. So, as we can see, coming down here, this will have an angular frequency. It will go through a certain angle in a certain time, so we can describe the pendulum like we can describe circular motion. Omega still has the identity of 2 pi over t, and we know that acceleration, when we're talking about the pendulum bob, is equal to minus omega squared, should be a square up there actually, x. So what this is talking about, the reason that the negative sign is here, is because when the pendulum bob is at maximum positive displacement, its velocity is 0 and its acceleration is going backwards, hence the negative sign. So the vector for acceleration will actually point in the opposite direction to the displacement. This is at all points of the pendulum bob swing. Like we saw with the circle, I can describe x, the displacement, as equal to the amplitude times by cos theta. Now, at the moment, I don't know what this thing is, but I know that I've got a angular frequency, and I also know that I can measure time. So if I have a look at omega t, small t, so this isn't the time period now, this is just any measurable time, I can say that omega t equals this: 2 pi little t over big T. Now, these dimensions of time now cancel out and they leave me with just an angle. Remember, omega was the amount of angle in a given time. So I can say that x is equal to a cos omega t. And I'm absolutely fine to say that because that is an angle. Now, to get to this one, to get to the main equation, a equals minus omega squared x, to get to that, I need to get from displacement, a distance, to an acceleration. And I do that by differentiating. So if I say dx by dt, the rate of change of displacement is going to equal a velocity. How distance changes with time, that equals a velocity. And I'm going to differentiate this thing. I'm not going to tell you why it comes out to what it does. You'll have to look that up for yourself or come and ask. But this is then going to equal minus a omega sine omega t. Okay, then I'm going to have a look at how velocity changes with time. So I'm going to say dv by dt. Now, another way of writing that, just write this up here, is the second differential of position by time. It's also dv by dt, and that equals an acceleration. So I'm going to differentiate this thing again, and that equals minus a omega squared cos omega t. And that equals minus omega squared x. So we have our result. All we've done is we've looked at the displacement, we've related it to circular motion and related a time period, omega, and then we've differentiated this expression here to arrive at our equation for simple harmonic motion. This one is just a really important diagram that we need to know. So if I look at acceleration and I look at displacement, if this is maximum displacement in x, call that the amplitude, and this is sort of maximum negative displacement in x, call that negative the amplitude. When we have a maximum positive acceleration, we are at a maximum negative displacement. So that goes up there. And when we have a maximum negative acceleration, like we said here, we have a maximum positive displacement. So that goes there. And we have this very important graph which shows that proportional relationship between acceleration and amplitude. So that's simple harmonic motion. We're going to analyse this a little bit further in a later video.